Everyone. Sorry I can't be here today with you, but I'm going to go through everything that we would have done if I was there anyways. So if you remember last time we were together, we talked about Newton's first law of motion. So let me show you the definition for that just in case you haven't gotten it all the way down. It says an object at rest will remain at rest unless acted on by an unbalanced force. An object in motion continues in motion with the same speed and in the same direction unless acted on by an unbalanced force. So that unbalanced force piece is consistent, whether it's at rest or if it's moving, nothing is going to change that except an unbalanced force. All right, let's take a look at Newton's second law now. I do like this video much better than the one that I started showing you yesterday.
Let's look at Newton's second law of motion. Have you ever pushed a lightweight object across the floor? Pretty easy, right? Have you tried to push a heavy object? It's no surprise that it's more difficult. What about pushing a really heavy object? It's nearly impossible, isn't it? The more massive the object, the more force you need to move it or change its direction. Here's the formal definition of Newton's second law. It's a simple equation. Force equals mass times acceleration. Acceleration means to speed up, slow down, or change direction. Let's break down the equation. Force and mass are directly related. The bigger the mass, the bigger the force needed to move it or change its direction. You just saw that with all those pushing examples. Force and acceleration are also directly related. To get a large amount of acceleration, you'll need a big force. A car with a more powerful engine has greater force than a car with a weaker engine. With two cars of about the same mass, the one with more force produces more acceleration. It can speed up faster. Now let's think about a cool game, pinball. The flippers inside a pinball machine hit a marble, accelerating it from rest to zipping through the game fast. What if the flippers used the same force to hit a much more massive bowling ball? How much would the flippers change the ball's speed? Not much. Mass and acceleration are inversely related, meaning when one is large, the other is small. For the same force, a tiny mass accelerates a lot, and a big mass accelerates very little. Sometimes you don't want to change an object's speed. You just want it to point in a new direction. The force of this roller coaster track makes the cars keep changing direction, causing them to move in a circle. Otherwise, by Newton's first law, they'd want to keep moving in a straight line. So, when it comes to Newton's second law, this simple equation, force equals mass times acceleration, can help you solve a lot of interesting problems, including many in flight and space.
All right, so let's go ahead and I do want to show you one more video. That's a really good one. It's actually in space, so there's no friction or anything like that that can interfere with Newton's second law. So let me show this to you. And we're going to be doing our space unit in a few weeks, probably like 4 weeks or so, and so this is a good lead into that.
Hello, everyone. I'm astronaut Randy Bresnik, living and working aboard the International Space Station. Now, on the space station, we live in a microgravity environment. Do you think the laws of physics will hold up? Come on, let's go find out.
The acceleration of an object depends on the net force acting on the object and the mass of the object, or F equals ma.
Jolly good show, Sir Isaac.
Here we see that once the force of the thrust is greater than the weight of the vehicle, the rocket begins to accelerate.
All right, we're going to start with something small, something you might have at home. A little stick of chapstick. And use our force being our bungee cord here on our bungee, and we'll pull it back. And you can see how fast it accelerates because there's very little mass. Next, we'll try a little spaceship. A little more massive, and you can feel that because as you move it, you can feel that the kind of force, the extra force you have to push with your hand. So we'll put our spaceship on our launcher here, same spot. Notice it's flying a lot slower than that chapstick did. What we've seen is the same amount of force on a smaller, less massive object means the acceleration is faster. Well, this is the biggest and most massive thing we have. So let's see how the acceleration is affected. At the same amount on the force. And here we go. There you have it. Newton's second law of motion in action. Thanks everybody for exploring a little physics with me today. Now I'm going to send it back to Earth so you can start your experiments. See you again real soon.
All right, wasn't that cool to get to see how Newton's second law plays out in space? You could definitely see that the more massive the object, the more force it needed to accelerate that object. So I'm going to have you guys record your the definition for Newton's second law in your Project Lead the Way notebooks. Okay, you do not need to worry about the equation because for the purposes of this class, we're not going to be dealing with the equation. I just want you to understand this definition right here. Only the highlighted part you need to write down. So it says Newton's second law, acceleration is produced when a force acts on an object. The greater the mass of the object, the greater the amount of force needed to accelerate the object. Okay, so just this highlighted part, go ahead and record that in your Project Lead the Way notebooks. Feel free to pause it if you need more time, but I'm going to move on. Okay, let's take a look at Newton's third law of motion. This video for you.
What can you do with your Prodigy membership? You can rescue and evolve all of...
The only question you need to ask yourself while studying the third law is, what happens when two objects interact with each other? What happens when you place an object on the table? The object exerts a force on the table, and the subject exerts an upward force on the object. There are two forces that result from this interaction, a force on the table and a force on the object. The magnitudes of the two forces are the same, but the directions are opposite. These forces are called as action and reaction forces. The force exerted by the object on the table was an action force, and the force exerted by the table on the object is the reaction force. What we saw here is nothing but a display of the Newton's third law of motion. Every action has an equal and opposite reaction. That's how simple the third law is. Every action has an equal and opposite reaction. It means that when two objects interact, there is a force on each object. The magnitude of force on the first object equals the magnitude of force on the second one. And what about the direction? The direction of force on the first object is opposite to the direction of force on the second one. Let's talk about more examples. While a frog is swimming, it pushes the water back and the water pushes its body forward. Now let me ask you a question. Say a bird is flying upwards. Will the Newton's third law apply here? Sometimes the third law is not so obvious. You'd probably say that the bird is the only object here and there's no second object. But that's not correct. The wings of the bird push the air downwards, and the air pushes the bird upwards. Action and reaction forces make it possible for birds to fly. We take one last example to understand something very interesting about the third law. What happens when a gun is fired? You're right, it exerts a forward force on the bullet, and the bullet exerts an equal and opposite reaction force on the gun. And this exists in recoil of the gun, a perfect example of Newton's third law. But hold on, if the force exerted by the gun on the bullet is the same as the force exerted by the bullet on the gun, then why doesn't the gun recoil with the same acceleration as the bullet? The gun recoils, yes, but it doesn't recoil at the same acceleration as the bullet, right? Same magnitude of forces, but different accelerations. Why do you think this happens? Okay, so if your concept of the second law of motion was clear, you wouldn't really be surprised with this. The second law of motion says that the force is the product of the object's mass and acceleration, or the acceleration of the object is equal to the force over its mass. What does this tell us? Yes, if the mass is more, then the acceleration will be less. In this example, the mass of the gun is much more than that of the bullet. Hence, the acceleration of the rifle is lesser than that of the bullet. If you're in a boat and step out of it onto the land, there are two forces involved. You pushing the boat behind and the boat pushing you forward. And that's why you see the boat go behind when you go forward. Now let's say a sailor jumps off a huge ship. The sailor does apply a force on the ship, and the ship also applies a force on the sailor. But do you think the ship will accelerate as much as the sailor? Not really. And I think you know why.
Okay, so on that last example, the ship is so massive that the force exerted by the man jumping off the ship moves the boat very little, okay, because it takes a lot of force to move something so massive. So I'm going to have you write down in your Project Lead the Way notebooks, the definition for Newton's third law is for every action, there is an equal and opposite reaction. So go ahead and record that. And then I have one more video to show you demonstrating Newton's third law. You can pause it if you want to finish writing this down. All right. This is another one of in space, which I think is really interesting. It's going to show us what Newton's third law looks like in space.
Good grammar and spelling are important, but if you want to write essays that inspire,
Welcome to the International Space Station. I'm NASA astronaut Mark Vandehei. Today, we're going to talk about Newton's third law. How do you think it will hold up in microgravity?
For every action, there is an equal and opposite reaction. This means that in every interaction between two objects, there are a pair of opposite forces acting on each object at the same time. A force pair. You can see that there are many examples on Earth. In space, thrusters expel one way and the vehicle is steered in the opposite way.
Hello again. More basketball stunts that I can't do on the ground, at least not while getting this much hang time. All right, back to serious business. We've got a basketball right here. It's going to be object 1. I'm the second object. If object 2, myself, applies a force to object 1, then that same force will be applied according to Newton's third law by object 1 onto object 2. However, there's a big disparity in the mass. Object 1 is a very light mass object. Object 2, myself, is a larger mass object. So I'm going to try to make myself about the same shape as this ball. See how that works for us. And I'm going to apply that force. you saw that force applied to the ball made it accelerate quite a bit. It really didn't accelerate me much at all. Newton's third law again, but this time we're going to use two similarly massed objects. Joe and I have about the same mass. So Joe, get into a ball. I'll do the same. I'm going to face you this way so I don't throw you into something you can't see. Now I'm going to get into a ball behind Joe, and I'm going to apply a force to him. Notice that when I applied a force to Joe, it accelerated Joe away from me, but I got accelerated away from him as well, because the force applied to Joe ended up being the same force that was applied to me. Now you've seen Newton's third law in space. Now test it out on Earth. See you next time.
I sure love those space videos. They're awesome. So let's go ahead, and you guys have already written the definition down for Newton's third law. So now we're going to take a look at what that looks like for a plane. So I'm going to scroll up here. Actually, if you could please, I would like you to pause this video and answer the questions that I posted in the Otis lesson. So after this video, you're going to see a couple of lesson tiles that are asking you questions. Go ahead and answer those questions. Again, please answer in complete sentences. Okay. So let's take a look at what these forces mean for flight. Okay, so as you know, Newton's laws describe the relationship between an object and the forces acting upon it, and the object's motion in response to those forces. Multiple forces pushing and pulling on the plane affect the plane's speed and direction. Okay, so I'm going to have the sub pass these out at the beginning of class, so hopefully you have these already. You're going to find a space in your Project Lead the Way notebook. You might not have space on the current page you're on, so you may want to turn to the back side and put this plane in the middle. You can either glue it down or just tape it on real quick to the middle of your page, and then add these arrows to it. And what we're going to do is we're going to be exploring what each one of these forces are, because there are 4 major forces acting on an aircraft. Okay, first 2 forces. This first force right here is called lift. It is the upward force that enables an aircraft to rise off the ground and remain in flight. This force, lift, is working against gravity, the downward pull of gravity that we call weight. So in your Project Lead the Way notebook, you have your little plane and you have your arrows. So the arrow that's pointing up, I would like you to label this lift. The airplane that is pointing down, I would like you to label this weight. So those are the 2 forces that are acting on an aircraft. Feel free to pause at any time if you need more time. Now, let's take a look at the next 2 forces that are happening to a plane. Okay, first of all, we have thrust. So this arrow that is pointing in the direction that the plane is going, this is the thrust. The thrust is the force that propels an aircraft forward. And that's usually the thrust is usually created by the engines on the aircraft. It pushes it forward. And the opposite force here is drag. So the arrow that's pointing in the opposite direction that the plane is moving is called drag. And this is the force of resistance that works against the forward movement of the aircraft through the air. Remember, there's air resistance as you're flying, and we call that drag. Okay, so you should have all 4 of your forces on your Project Lead the Way notebook. And mine's kind of messy because you'll be adding some more to it later. But here I have the lift, the weight, the drag here, and the thrust. And then what we're going to be doing next is we're going to be going through and labeling all the different parts of the aircraft. I don't believe that we have time for that today, so we're going to go ahead and wrap it up here. But be prepared tomorrow. We're going to go through and label all the parts of the aircraft. All right, guys, sorry I couldn't be here today, but email me if you have any questions and we'll continue on tomorrow.